Hello, and thank you for joining me today as we finish up chapter 15, talking about chemical equilibrium. We're going to talk about Chatelier's principle today and how equilibrium shifts when reactions are changed after they've already reached equilibrium. So, for starters, Le Chatelier's principle states in words, if a system at equilibrium is disturbed by a change in either temperature, pressure, or the concentration of one of the components, the system will shift its equilibrium position so as to counteract or negate the disturbance. And that's a lot of words, doesn't make a ton of sense, kind of hard to follow. So let's do some talking about what this exactly means. And so with Le Chatelier's principle, we have a system at equilibrium. So this system is at equilibrium here. You notice the size of the objects. If I shift this equilibrium, so you notice the pink box stays roughly the same size, my blue box was the same size, is now bigger, and my yellow box stayed the same size. So I added some of this substance. I added some of this blue substance. What happens then is I have to get rid of some of my blue substance. So both my blue and my pink are going to decrease because I'm going to push the reaction to the right. I'm going to favor the forward reaction. And so this one is going to go up. So I produce more products to get to my new equilibrium value. So that's a change in concentration. If I change the pressure, so when we talk about gases, we can change pressure. When gases go from an initial state of equilibrium, if the pressure changes, if the pressure decreases, it pushes to the side with the fewer number of moles. Let's do it that way. Fewer number of moles. And we're going to look at this in a second. But you're basically going to add up all your coefficients. And if you have a total of 3 on the left and you have a total of 4 on the right, if I add pressure to this system, it's going to push this way because 3 is smaller than 4. And your last one that we're going to look at is temperature. So temperature, if I have an endothermic reaction and I increase the temperature, I'm going to shift the equilibrium to the right. I'm going to push towards the products. I'm going to produce more products. I'm going to favor that reaction. If I decrease the temperature on an endothermic reaction, I'm going to favor the reverse reaction. I'm going to produce more reactants. And it's flipped for exothermic. So if I increase temperature on an exothermic reaction, it pushes towards the reverse reaction, the reactant side. And if I decrease the temperature, it's going to push towards the product side. If we're looking at concentration changes, so if we have a system at equilibrium, for example, this system is at equilibrium here. This is my H2 plus N2 plus 3N2 produces 2 NH3. Whoops. I missed on my coefficient here. 3H2 plus N2 produces 2NH3. Okay? If I add hydrogen to this system, so I added some of this substance. Because I added reactant, I need to produce more product, which means this is going to push to the right, which means that my hydrogen concentration is going to go down. My nitrogen concentration is going to go down, and my ammonia concentration is going to go up. So that's what we're seeing here. I added this hydrogen, and then you notice it dropped. My nitrogen, I didn't change at all, but it also dropped. And my ammonia, I didn't change initially, but it went up. So if you remove or add some reactant, you're going to change this concentration. So that's what's going on here. Let's go back to the volume and pressure so we can see this. So when gases are involved, we can change either the pressure or the volume because remember those two are inversely proportional according to Boyle's law, in which P1 V1 equals P2 V2. So if you have a higher volume or a lower pressure, ooh, that was bad. Higher volume or lower pressure, you are going to favor the side with more moles. You made more space you want more moles. So in this reaction, I have 2A, which is a gas. Sorry, not plus. Reversible reaction with B, which is also a gas. Notice I have 2 moles of A for every 1 mole of B. If I make a bigger volume or I decrease the pressure, notice that I have a lot more A dots over here than I do B dots because it favors that reaction. So it's going to push to the left, it's going to produce more reactants. On the contrary, if I decrease my volume, increase my pressure, I have much more B molecules, B atoms than I do A. And that's because there is a smaller coefficient here, a smaller number of moles for B. So that is how pressure and volume change the concentration or affect the equilibrium of a gaseous mixture. If we change temperature, we need to determine whether the reaction is endothermic or exothermic, and that is really important. We have to determine that first. For example, if you have A plus B produces C, if this is exothermic, I'm going to write heat just as its own separate substance, as its own component. Then I can treat this just like everything else. So if it's exothermic, heat acts like a reactant. If it's endothermic, heat acts like a reactant. Adding heat drives the reaction toward the product. If it's exothermic, heat acts like a product. So in this case, this is exothermic. Because I'm producing heat, this is exothermic. So adding heat is going to drive this reaction toward the reactant side. So I like to think of it as a big circle. That I changed something on the bottom. So I added my heat. What that's going to do is going to push the reaction in this direction, which means that these two are going to increase, and these two are going to decrease. Because it's favoring the reactant side, I have to lose heat and I have to lose some of C. So that is an example of how that works. Here is an endothermic equilibrium. So you have this substance here, which is cobalt, cobalt bonded to water is what it is, and it's reacting, or it's with chlorine gas, or chlorine ions. This is cobalt chloride dissolved in water. There we go. And it produces, on this side, we get cobalt chloride plus 6 water molecules. Now, because delta H is greater than 0, my change in energy is greater than 0. That means I'm gaining energy. I can add, for mine, I would add plus heat on this side. So heat plus this, plus your cobalt, or plus your chloride, produces cobalt 4 chloride and cobalt 2 chloride, and 6 waters. Okay? So I can treat heat just like the rest of it. So if I remove heat, I'm going to pull heat down, and then it's going to come clear over this way, which means I'm going to favor the reverse reaction here to produce more heat, which means that this is going to go up, this is going to go up, this is eventually going to go back up, and these are going to go down because they're favoring the reverse reaction. Now if I change this, if I would add heat, this is going to favor the forward reaction, which means that these are going to go up, this is going to go up, my chloride is going to drop, my cobalt is going to drop, and my heat after it's added is going to then drop. For exothermic equilibrium, we have the Haber process, which produces ammonia. We're going to look at that on the next slide. This is an exothermic reaction. So you would think that cooling it down would result in more product, but the activation energy is really high. This is the one instance where a system in equilibrium can be affected by a catalyst. So this is the one example where, because you have such a high activation energy, cooling it down is not going to make more product. And that's due to that, again, high activation energy. All right, let's look at this reaction now. Okay, so we have our ammonia here. Okay? And so what's going to happen is if I would add nitrogen to this reaction, I want to know what's going to happen to the equilibrium. Is it going to shift left, right, or not at all? And so if I add nitrogen, which means this goes up, because that goes up, it's going to push this way, which means my hydrogen concentration is going to go down, my nitrogen concentration is eventually going to go down, my ammonia concentration is going to go up, and I'm going to make more heat. So this favors your products or forward reaction. Okay? If I add ammonia, if I do the opposite, so if I would do the opposite, if I would add ammonia instead of nitrogen, I add here, which means this is going to push to the left, which means I'm going to increase my nitrogen concentration, increase my hydrogen concentration. Ammonia is then going to decrease, and I'm going to cool this reaction down. So this is reactants favored or reverse reaction. Either way works. You can try these two. Again, ignore the activation energy for this one. Just treat it as normal. Let's see what you do. See how you do on those. And I will get my drawings out of the way for you. But that is an example of this equilibrium and where we're going with it. All right. And so the last little bit is talking about those catalysts. And so a catalyst increases your rate of both the forward and the reverse reactions. Doesn't matter which way, a catalyst is going to increase that rate. Because equilibrium is achieved faster, but the composition remains unaltered. So we get to equilibrium faster, but it doesn't change how equilibrium happens. What you're doing is you're lowering your activation energy, which allows this to be established at lower temperatures. So instead of having to come all the way to the top here for your activation energy, you only have to come up this high, which favors a faster, so it means more molecules can react quicker, which gives you a faster equilibrium concentration or equilibrium turnout. But that is it for your chemical equilibrium notes and information. We will do some practice in class, and I look forward to working with you through the rest of this year.